Welcome to this episode of Real Chemistry. This is the fourth in a series of videos on calculating heat, work, enthalpy, and internal energy for changes in ideal gases. In this case, we're going to look at adiabatic expansion. So adiabatic is a strange sounding word, which basically just means that something's thermally insulated. So think here of a thermos. A thermos holds all the heat in, and if I did something to an ideal gas in a thermos, that process would be adiabatic. Or think of an insulated coffee cup. Again, there you don't allow thermal energy to transfer in and out, and that's an adiabatic process. In this case, we're looking specifically at an expansion of gas that is both reversible and adiabatic. So let's take a closer look at both of those words. So here is an example of what's going on. We start out here with a gas that is relatively compressed, and over time we expand its volume. So that's the expansion part. The fact that it's reversible means that we've produced this by small incremental changes. We've slowly changed mass 1 to mass 2. And that slow incremental change allows it to be reversible. We can go back and forth in this process. Adiabatic, remember, means that there's no transfer of thermal energy. What that doesn't mean is that there's no change in temperature. There is a change in temperature precisely because the walls are insulated. So what that means is Q, if I think about the heat that would flow out, Q has to be 0. And that's always true for adiabatic processes. There's no transfer of heat out. However, temperature will change. In this case, because we saw the piston expand, that's going to tend to drop temperature and drop pressure. So we should see a decrease in temperature, a drop in pressure, but heat, our Q, will be 0. Because remember, Q is about the transfer of heat, and that's what we're making 0 by making our process adiabatic. All right, in adiabatic processes, there's a few extra equations here that we're going to use. One allows us to go between the initial and final temperature for an adiabatic process, and another one allows us to calculate work. I'm not going to go through the full derivations here, but I'll link below two derivations for both of those equations that you can take a look at. Those do represent extra equations that you got to know since they're not coming just from these standard equations here on the right. Okay, let's go ahead then and calculate Q, W, delta H, and delta U. The easiest one, you should already know the answer to it because we just talked about it. If there's no transfer of thermal energy inside or out, then we know Q is 0. And that gives us a good head start for finding all sorts of variables. We have one piece, for example, of our first law of thermodynamics. Next, because we have this nice equation, let's go ahead and calculate work. Here's the tricky thing. If I want to get work, notice I need this change in temperature here. However, the bad news is it only tells me the initial temperature. And that's why I need my equation here that relates temperature 1 to temperature 2. So the first thing we're going to do is find temperature 2, and then we'll go ahead and plug that into the work equation. So if I use my equation on the bottom left here for temperature 1, relating it to temperature 2, I'm going to plug in temperature 1, which I know is 272 Kelvin. I'm going to multiply that by volume 1 over volume 2. Volume 1 is 2.0 liters, that's where we're starting, divided by volume 2, 3.7. And then I'm going to raise that to negative R over CV. So negative 8.3145 divided by 3/2 times 8.3145. For an ideal gas, that's the heat capacity as we have listed over there. Now, the trick here is this is actually going to have the 8.3145s cancel out, and then we'll get the reciprocal of the 3/2. So we're really going to be raising that all to 2/3. Oops, 272. 2.0 divided by 3.7 raised to 2/3 is going to give us our new temperature, which is 180.5 Kelvin. Okay, so that's our temperature 2. That's our final temperature. All right, so we found our temperature. We found our Q. Let's use that temperature to now find work. Work equals NCV delta T. N in this case is 1.2. CV, the molar heat capacity at constant volume, is 3/2 times R. Oops, let's make that a little neater. Times my change in temperature, which is temperature final, which I now know is up here at 180.5, minus temperature initial, which is 272. What I'm going to find then, that work rounded to 2 sig figs is negative 1400 joules. So that's work. Okay, now we have work and heat. So what can we calculate? We can calculate delta U. Delta U is equal to Q plus W. So delta U is equal to 0, which is my heat, plus work, which is a negative 1400 joules. And what we're going to get is that delta U is negative 1400 joules. Ta-da! There is delta U. Except for something that's helpful is to actually write the variable down. So we're going to do that. Perfect. All right. So lastly, let's calculate enthalpy. We have our enthalpy equation right there. Delta H is equal to delta U plus delta PV. Same trick here where we use the ideal gas law. We're going to plug in the nRT. It's like that should just be the version of the equation that is always used. But anyway, we're going to do delta H equals delta U plus delta nRT. And just like we've seen before, the only thing actually changing here is temperature. And so we can change this to nR delta T. All right, so delta H is equal to delta U, which we know is negative 1400, plus moles, which is 1.2, times the gas constant, 8.3145, times delta T, which is my 180.5 minus my 272. That's going to give me my change in enthalpy, which is negative 2300 joules. Boop. Okay, so that is enthalpy, internal energy, heat and work for an adiabatic process. Remember to check out the links below to see the proofs for those two equations that we took advantage of. And here is the summary for all of our different circumstances where we can calculate Q, W, delta H, and delta U for ideal gases. Remember, this is just for ideal gases, and so these calculations can become more complicated if they use real gas equations or are for other substances. Thanks for watching this episode of Real Chemistry. You can subscribe below or comment if you have any questions.